It turns out polar coordinates has actually two reasonable generalizations in 3D. The first one is called cylindrical coordinates. And in cylindrical, we have this. You can think of this sort of like polar plus a z-axis. So the same two identities hold. X equals r cosine theta, y equals r sine theta. And z is just z. It doesn't involve the theta at all. The r and theta are just in the xy plane, and the z is just z. So now this gives you a good way of taking something in polar coordinates and in cylindrical coordinates and converting it back into rectangular, because x is in terms of r and theta, y is in terms of r and theta, z is in terms of z. So here, x, y, and z are in terms of r, theta, and z. So this is actually a good way to take cylindrical coordinates and change them to rectangular. But oftentimes we want to go the other way around. So we're going to do the usual polar trick. If we take the first two equations, square them, and add them together, you get x squared plus y squared equals r squared. If you take the first two equations and divide them, the y equation by the x equation, we get y over x equals tangent theta. And then the last equation is just going to sit as is, z equals z. So this is the way to go from rectangular back to cylindrical coordinates. Those three equations. So there really isn't much more to do other than maybe try some examples. We're now going to look at the other generalization of polar coordinates, and this is spherical. Now this is maybe a little bit harder to see. I'll try to draw a reasonable sketch here. So here we have three new variables: rho, theta, and phi. Now we'll start with theta first. That actually is the same as the polar angle theta. So if we were to look in the xy plane, theta is the angle from the positive x-axis. So this is the usual polar angle. If we look at phi, well, phi is the angle of descent from the positive z-axis. So another diagram, if this is the xy plane, we're looking at a cross section now. If this is the z-axis, your angle phi represents how far descended you are from the positive z-axis. So this is angle of descent. Now, before we go on to the rho, something we want to note on here is that theta can take on values from 0 to 2 pi, and phi can start at 0. If we're totally up on the North Pole, it's at 0. Phi increases as we move along in this direction, but if we ever go past pi, that's actually in the turf of just turning around. It has more than one representation. If we want to keep a representation unique, we're going to keep this less than or equal to pi. So phi goes from 0 to pi, though theta goes from 0 to 2 pi. And then rho is sort of like the new r. This is the distance from our point to the origin. So if we realize this in x, y, and z coordinates to translate from one to the other, x is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi. Now if we want to figure out, so this again is a good way to go from spherical back to rectangular again. If we want to go the other way, we have to do a little bit of solving. First up, we've got a lot of trig in here, so we can probably rely on some identities. If you take x squared plus y squared plus z squared, if you square all these and add them together, well, everything's got a rho squared in common, so we could factor that out. Then we've got sine squared phi cosine squared theta plus sine squared phi sine squared theta plus cosine squared phi. Now that looks kind of like a mess. To simplify this, if you look at the first two terms in here, these both have a sine squared phi in common. So let's factor that out. So that gives us sine squared phi times, and then what's left over after we factor it is cosine squared theta plus sine squared theta. And then we've got this extra cosine squared phi at the end. Okay, and now cosine squared plus sine squared is 1. So this is out of the picture. We're left with rho squared sine squared phi plus cosine squared phi. And again, this is 1. So that's out of the picture, and we just get rho squared. So that was a lot of work just to say that rho squared is the sum of the squares of the x, y's, and z's. So that gives us our first spherical identity, is that rho squared is x squared plus y squared plus z squared. Okay, now from here, if we also say wanted to get theta, well, again, we can do that trick where we divide the x and the y. So if we take y divided by x, this is rho sine phi cosine theta divided by rho sine phi sine theta. We can see we've got a bunch of cancellation. The rho's cancel, the sine phi's cancel, and this gives us that y over x equals tangent theta. So that gives us our second identity. Now if we want to get the phi, that's the only thing left over. If we look at each of the three equations right here, the simplest one to solve for phi would be the last one, because it involves the fewest number of factors. So if we go and solve this, we've got z equals rho cosine phi. Well, we can divide by rho equals cosine phi. And now rho, we actually figured out from before, is the square root of x squared plus y squared plus z squared. So this says that cosine phi is z over the square root of x squared plus y squared plus z squared. So this gives you a way to solve for phi, solve for theta, and solve for rho. So this is how you convert from rectangular coordinates to spherical coordinates.